To start again, we all know about cryptography. It's a study of how to protect your data. Basically, by having a secret key, that someone can protect their secret data by transforming into a message which looks indistinguishable from random garbage, random data. So theoretically, this should be secure, given that if the attacker cannot recover the secret information, the data could not be retrieved. However, this security is only work in a theoretical setting, because once the algorithm has been ported on the target device, any computation itself may leak some information. This can be exploited non-invasively by an adversary. For example, someone can just tap into the wire to measure the power, or measure the electromagnetic emanation, or even to measure the timing execution of an operation. These attacks are very powerful, and it has been shown to be practical. For example, some reported attacks on keylock, Bitcoin wallets, and even on recovering the secret key of bitstream encryption on FPGA. So the main application of these attacks are for secret key recovery. So because, as we know earlier, that if the attacker can recover the secret information, the secret key, the whole encryption system is gone. So this side channel analysis possesses a serious threat for embedded systems. So some observation that we can see is basically in previous works, most of the attacks have been reported or tested on a development board, such as AVR or ARM devices. These devices have a very low noise, which is pretty easy to attack. And also, there are some reported attacks on the commercial devices, but these attacks are very target specific, and sometimes it requires a very specific knowledge in order to perform the attack, either through a reverse engineering of the device, or some more in-depth analysis. So one of the key challenges in performing such channel analysis, can it be practically applied on a real-world target, where for example, multiple operations are running in parallel, which resulting in a noisier or more desynchronized measurements. So what we work here is, first of all, we want to say that conducting such channel analysis attack, basically most of the attacks have been done on AES. In this work, attacking AES is not the main objective of our work. We are instead focusing more on evaluating a practical attack in a non-ideal or non-scenario. So when we're considering non-ideal or practical scenario, the main challenges is to find a target device. We decided to perform performing an attack on the target devices, ARM Cortex-A72, which is commonly used on different devices. Sorry. The devices itself, although it's a bit old, we consider it as a representative of what most of the devices is being implemented today. And as such, by investigating this, it could help us in understanding better understand what are the practical challenges that we may encounter. Some additional difficulties which we consider when comparing to previous target is that there will be operating system running, interfering with our measurement. There will be out of order execution. There will be noise from the input-output port, and so on. So this will be our main target, ARM Cortex-A72. Two of the main components which we think that will be hindering our experiments is the multiple cores, because it has 1 to 4 cores, and most likely when it's running in parallel, it added noises to the measurement, and the processor itself is running out of order execution, meaning that due to some optimization, sometimes even the same sequence will not, same operation will not be executed in sequence, and it will cause us desynchronization in the measurement. So of course, the device itself, as we mentioned earlier, has been widely used for different applications. In this case, we will be focusing our experiment using Raspberry Pi 4B as our main target. So to give our contributions, basically we conduct a comprehensive side channel on AES on Raspberry Pi 4B, which utilize ARM Cortex-A72. We highlight the key challenges which we described earlier, such as we encountered noise, jitter, OS interference, and out-of-order executions. We consider multi-level threat models. Basically, we consider different level of adversarial knowledge. This helps us to understand the difficulty or effort required by an adversary to perform the attack in such a complex processor. And as a byproduct, we also present a novel AES dataset we collected from this processor. We presented as a public dataset for chess challenge, and then this public dataset can be used by anyone, and hopefully can help advancing explainability for such channel research. So this is our experimental setup. First, we consider our target device, Raspberry Pi for model 4B on the right side, and then we implemented AES. It's a basic C implementation, unprotected and with mask implementation. We conduct EM side channels, so we use a rescue EM probe with an inbuilt amplifier to improve the trace quality, which we capture using LaCroix oscilloscope. We consider two attacker scenarios, profile and non-profile attack. To recap, the key challenges for this experiment is we consider first the presence of noise due to the other operations running in the background, and out-of-order execution, which, as we show later on, will lead to inconsistent waveform pattern. Finding the ideal probe position is also non-trivial because, as again mentioned, it's due to desynchronization and due to the noise level. It's very hard to find exact point where we put the probe, and as such, we have to do trial and error and do several pre-processing to identify area of interest. Pre-processing methods itself are also required for handling the desynchronization. We tried several pre-processing approaches, and then we found two which works for our scenario. The first is we perform trace filtering. Basically, we capture a set of traces as well as their trigger length, and then we do a statistical analysis on the trigger length. We identify which length occurs the most, and then we filter our traces based on that. And the second is we use realignment method. We use elastic alignment to realign the traces to get a better to improve the quality. And of course, due to all these challenges, more traces will be required for our attack. So for the measurement, this is the zoom out of our chip where we put the probe. We perform a grid search to best identify the area of interest for putting the EM probe. We first put multiple AES running in sequence to first identify area where AES at least are visible. So we use a visual inspection, and on the middle, we finally find an area where we can identify at least 10 rounds of AES. However, even then, when we zoom out, we still see a high desynchronization level. So in this case, the operation we might be observed at least 10 rounds, but we still cannot identify precise positioning. So for the measurement, we further do leakage assessment to do initial assessment. We do TVLA, SNR, which is a commonly used method. We could not identify any presence of leakage. So the dataset itself, we collected 3 different datasets, 2 of which is only considering the S-box operation. The first one is unprotected AES S-box, and the second is masked AES S-box. And the third one is basically we capture the full AES unprotected implementation. So as shown in the figure, basically TVLA doesn't give any leakage point. And for SNR, there's a peak which we can observe. However, when we see at the SNR value itself is of value 0.008, which might not be significant. So these are the threat models that we are considering for our experiment. We consider 3 adversarial models. With basic adversary is doing the adversarial with the lowest knowledge. We basically has no prior knowledge about the implementation. The adversary can only perform a non-profile attack. So basically, he only knows simple leakage model basically is a textbook attack. For example, you can do correlation power analysis or CPA with only Hemingway or identity leakage model. The next one is educated adversary. In this case, the adversary has a priori knowledge about the countermeasure. For example, he knows that there's a desynchronization happening, so the attacker can perform CPA by first realigning the traces. And lastly is the advanced adversary. Basically, the attacker has access to clone devices and can build a profile attack. In this case, it's considered the highest the adversary with the highest knowledge. For example, they can do a template attacks in this scenario. So to compare with previous works, our current work basically, as mentioned, we considered ARM Cortex-A72, which compared to other previous work is the only chip which run out of order execution. And as you can see also from the list, most of the previous works are focusing only on uneducated attacks. There's one related work which also focused on an advanced attack which targeted iPhone 7. However, the processor they use, the ARM Hurricane, is a very customized target. Basically, the authors need to develop a special measurement setup. It took a lot of traces and a lot of resources, and as such is not a standard attack. Nevertheless, in this work, again, we emphasize that we are considering multi-level threat model. We are investigating how different attacker model can deal with this kind of practical scenario. So to start with, we consider a basic adversary attack. So as mentioned, the attacker can only perform a basic CPA with a simple textbook leakage model, Hemingway or identity leakage model. No pre-processing can be performed. So we tried it on all the data set, and in the figure we show it on the simpler scenario, the raw one Xbox implementation. As I can see, we perform CPA. The correct key is highlighted in the green color, and ideally, if the attack is successful, if this leads to the highest correlation, but as can be seen, the correlation with the wrong key candidate with the red color has a higher correlation. So in this case, the attack is unsuccessful. As we can also note that similar to the previous SNR figure, the position is the same. So basically, the leakage is coming from other operation which is unrelated to the key that we are targeting. So in this case, again, to summarize, for basic adversary, it leads to unsuccessful attacks. So we move next for the case of educated adversary. In this case, the adversary can perform CPA. We consider two realignment techniques, namely the elastic alignment and trace filtering. Again, we show the result for CPA on the aligned traces. The correct key is not cannot be recovered. Again, for educated adversary, the attack is unsuccessful. Lastly, we consider the cases for the advanced adversary. Basically, the adversary can get access to a clone device and build a profile of the device. So in this case, we consider first to try template attacks. However, due to the desynchronization issue, template attack in this case does not work because even after realigning the traces, the key cannot be broken. Instead, we use another approach, namely using deep learning, which is commonly used nowadays for inside channel. It has been widely used in different attack scenarios, and it has been shown that it can tackle masking and desynchronization. So we consider deep learning-based side channel analysis, or DLSCA, is a suitable candidate for this approach. One of the observations is that in the previous work, most of the DLSCA attack that are reported has only been tested on a low-end microcontroller or a low noise target. So we also investigate how in this experiment to see how good it is for DLSCA on a practical scenario. One of the challenges in conducting DLSCA is finding a proper parameter. Our solution is to use a random parameter search. Basically, we use a CNN model. For the architecture, we use a random parameter, so we have a sample size for different batch size, learning rate, and so on. So we train 100 different models. We evaluate the performance and choose the model with the best performance. To evaluate the performance, we use the guessing entropy and NTGE as the evaluation metric. Basically, guessing entropy indicates that on average, what is the rank of the correct key. So guessing entropy of 1 indicates that the correct key is ranked first. So, and NTGE indicates is how many number of traces required before it reaches guessing entropy 1 and stabilize at 1. So on this figure, we show the experimental result with 100 random models. As we can see, for the best model, it reaches guessing entropy 1 at 21,626 traces. So basically, this we record our NTGE as 21,696. The NTGE less than infinity basically indicates that the attack is successful since the key can be recovered. So when we consider doing the attack with DLSCA, we show the result for multiple scenarios. We also, in addition to doing the attack, to do the attack on raw traces, we also perform the attack on the filtered and aligned traces with EA. And as we can see, in all scenarios, the correct key can be successfully recovered using DLSCA. And for the number of, for the NTGE, which means the number of traces, we can see the clear pattern that for the basic attack on the raw traces, for full traces it's harder to break, and for masked traces is the hardest in this case. And another observation, we can see that for the filter and aligned traces, they significantly, especially on the filtered traces, they significantly reduce the number of traces required. So it indicates that the pre-processing is useful in reducing the number of traces required. So as a discussion, in the discussion, basically we have observed that the pre-processing techniques help to improve the attacks. Another observation that comes out during the is that as more and more devices are incorporating advanced processors, it brings up the issue of cost versus security trade-off. So basically, we see that the SCA countermeasures are costly. However, as from our experiments show, an advanced adversary is required to break to even break an unprotected implementation on complex processors. So this brings up the question: what are the trade-off? How much, like what countermeasure is actually needed versus the cost that is for the implementation. Another thing is that since we are doing only a random search, for our future works, the questions that comes out is, can this attack be improved further by either using a better profile model, better pre-processing, or even will this attack still be possible in a more complex targets? So to conclude the talk, basically we have demonstrated the attack efficiency on a complex processor, extending previous work that mainly focused on the development board or microcontrollers. We highlight the key challenges in performing SCA on a complex target, complex processor with out-of-order execution, showing that practical attacks itself are not trivial to conduct. We investigate the effort costs required by the attacker to recover the key, and we show that advanced adversary is required to even successfully recover the secret key in the complex processor. And lastly, as a byproduct, we provide a novel public dataset collected from our experiment. So this dataset we have submitted as a part of a chess challenge. So the goal is either to give it to the public and maybe someone can do understand and investigate better, or even like if someone can try better, come up with a better model, and it can help with the advancement of DLSCA research. So we provide the QR code, it gives the link to the website, and it provides instruction on how to download and use the dataset. So that's all, my presentation. Any questions, welcome.